Yeah, so now it's time for Aleksandr, Sasha. He will talk about lattices of microresonators and all the nonlinearities happening there. Okay, so
Yeah. Hello everyone. Thank you, Mikhail, very much for the introduction. Can you see my screen? Just a moment. In presentation mode.
it's good.
Yeah, great. Thank you very much. So yeah, thanks again for the introduction, Mikhail. And so hello everyone. It's nice to see you. So unfortunately, it's still online, but I hope we'll meet soon in offline. Today, I'm going to present you basically some analytical stuff regarding the four-way mixing process in lattices of coupled optical microresonators. And basically, this work is motivated. So there is first a fundamental interest what will happen, because basically in Kerr microresonators, in single resonators, we know what's going on more or less. It's always the double balance between dispersion, linearity, gain, and loss. And so we pump it with a single laser, single line laser, and so as a result we get broadband spectra. So it's very nice. So, but for me, first of all, the first question that I would like to answer: what will happen with those solitons if we extend the dimensionality? If we consider a lattice of microresonators, and if we consider even more complicated structure as a topological lattice, even more. This also questions the whole topic is kind of important for dispersion engineering, because it will allow to control basically the dispersion of the whole structure, and as a result of the dispersive waves and the total width of the resonators. And so basically, let me jump straight to the general case of an arbitrary matrix. And I'm really sorry for the formulas here, but since I'm trying to justify my findings here, so there is no other way. But now use some more or less strict mathematics, kind of. Yeah. So imagine that we have a lattice of microresonators, for example, as shown on the bottom left corner, where each dot represents just a microresonator, which is nonlinear, and basically the dynamics of all the resonators will be described by the set of coupled Legendre-Lefebvre equations. You can see this equation shown schematically on the top, and basically the vector A it just contains field envelopes of all the resonators, and the matrix D is just our conventional dispersion plus detuning and loss components of a single LLE, and it's just a diagonal matrix. Matrix M here describes the coupling, basically the coupling structure between all the resonators, and so basically it will be the main interest. My main interest in the following, and also the nonlinear term. It's also a diagonal term. It's just typical cubic nonlinearity, which we'll see how it behaves when we treat this system. How can we treat the system? And the answer is pretty much simple. So we have a matrix, the coupling matrix M. It's an more or less arbitrary matrix, and basically, let's hope that it has a set of eigenvalues and eigenvectors, and those eigenvectors are orthogonal. So once we have once we use this assumption, we can decompose basically the solution, any state of resonators by just simply sum of all these eigenvectors with corresponding amplitudes. And in this case, the nonlinear term, remarkably, will already take form of a conventional Fourier mixing term of cubic complexity that we are used to see in coupled mode theory for just conventional Kerr microresonators. But if we just now use the property of orthogonality of all the eigenvectors, we can rewrite the equation on the top for the optical field envelopes of each resonator to the coefficients to the coefficients to which we basically decomposed the whole structure on the eigenvectors, and you can see the obtained equation at the bottom, basically, of the slide. And you can see the remarkable similarity of this equation to the coupled mode equation we are used to in a single resonator. Let's quickly take a look on it and directly compare them. So we have the first term, which is basically the loss term, and it's the same loss term that we have in coupled mode equations. Then we have detuning term plus detuning term, which basically depends on the frequency of the super mode of the special super mode that basically is just eigenvalue of the corresponding eigenvector. And the same thing happens in a single resonator case. So we have a detuning, it's described by alpha here, and we have dependence of the frequency of the Lth mode. And in the simplest case of just of a group where we can take into account only group velocity dispersion, it depends quadratically with the mode number. And here we can explicitly write it here for a single resonator, but for the lattice of microresonators, the dependence in general case cannot be described by analytical formula because it's always just decanalization of the matrix. Now, next, there is a term which corresponds to the, basically I've just discussed, to the dispersion, but it's chromatic dispersion of a single resonator. But you can now see how chromatic dispersion and band structure, how they have the same, basically, they affect in the same way the dynamics of the system. And the very last term, basically the nonlinear term, takes the form of, again, of the Fovich mixing process, basically as in a single resonator case. But the only difference here that you can see is that in just in a single resonator case, I mean, yes, of a ring resonator, the Fovich mixing processes, they have a very well-defined conservation law, which is basically represented by Dirac delta function under the summation. But in the case, in an arbitrary case of coupled resonators, this conservation law basically will be defined by the product of all the four, basically, eigenvectors in this form. And in this simplest case, it will just transform to the delta function, as I will show you further. Let's now quickly take a look on basically on the band structure of a already famous two-dimensional Haldane model, which has been already demonstrated in photonics already experimentally. And here I show you basically how the band structure looks like in the case of a lattice consisting of 21 by 21 microresonators. So what you can see here on the horizontal axis, I present the supermode index. Basically, it's just comb line index. It doesn't really matter. And on the vertical axis, it's energy and basically the frequency as well. And what do we have here? On this band structure, we have three remarkable regions. The bottom one and the top one, highlighted with white background, those are just bulk states, and you can see typical shape of the bulk state presented like these fancy carpets. So you can where each pixel corresponds to the resonator, and so by the resonator position in the lattice, and the color represents the amplitude of the electrical field. So we see that that electrical field basically redistributed along the whole lattice. But in the middle we have a special part where we have so which is called edge band, and at this edge band, what we have that the electrical field is concentrated only on the edge of the basically of the lattice, and it doesn't penetrate into the center. And what we can do with this, we can just try to we can plot the integrated dispersion of the edge band by subtracting the linear part of, for example, somewhere in the middle. And in the panel B here, I show in blue dots how this integrated dispersion of the super mode look like. So you can see that it's anomalous because the parabola goes up with the significant presence of the cubic term, and also cubic term probably. So basically all the Taylor terms you can imagine. And so the question here is, how can we describe the dynamics here? And the answer is pretty simple. Let's consider not two-dimensional system, but just one-dimensional chain. One-dimensional chain, and let's simplify it further. Let's consider it to be just equally coupled. And in this case, the band structure would be one-dimensional as well as the as the same as the band structure of edge states in two-dimensional topological model. And here I show the supermode dispersion of the edge of the basically of one-dimensional chain in red stars. And you can see the similarity here basically. So you can see it's anomalous. Of course, the presence of course, the difference between the models leads to the fact that the higher order terms of the dispersion, they are different, but anyway, by considering simple models, we already can capture the dynamics. And let me jump into this one-dimensional model. So in this case, what we have, we just have a system of coupled resonators, equally coupled, and the matrix now, I've been talking before, now it's just nearest neighbor coupling, like shown here in the red rectangle. And basically, so once we achieve to diagonalize this term, we get the celebrated cosine band structure. And this cosine band structure, we have two typical regions, anomalous and normal dispersion regions. As shown here, you can see that basically the eigenvalues I've presented you before just take form of a cosine. And this cosine, we already can use Taylor decomposition to basically see that basically, yes, we can basically see that at the edge of the band structure, so in the at the brilliant zone, we have anomalous dispersion. In the middle, it's normal. But let's not forget. But another simplification here is that the Pavich-Mitsyn processes now for supermode, they also simplify in the same way like for a single resonator, and now it's also a delta function. And now what happens now that the Pavich-Mitsyn process in this system, they are two-dimensional. They're happening on a two-dimensional dispersion surface, which has parabolic shape along the comb line index, as shown for interresonator dispersion with a coefficient D2, but it also has cosine shape in the supermode direction, leading to this complicated structure surface where basically, if we excite the parabolic type, the parabolic region, this parabola-like region, the modulation stability gain lobes would form on an ellipse. But if we excite the supermode in the saddle point, the modulation stability gain lobes would form on a hyperbola. This leads to the drastic change of the dynamics, drastic difference of the dynamics, even in already not in stable regime, but in a chaotic one. So on the left, you can see on the top panel, you can see the animation basically of the field profile. Is just simulation in time in the elliptic region. This is corresponding to dimensional spectrum on the bottom. And on the right, the same basically happens with the same pump power in the hyperbolic. You can see the drastic difference because in the elliptic region, impulses, they are forming and compressing rapidly than decaying. And the instantaneous spectral profile, I mean spectral in the comb line and supermode directions, has a shape of a disk. And on the opposite, in the hyperbolic regime, there is no quick compression and dissipation of the pulses because we have anomalous dispersion along phi axis, so comb line indexes, and normal dispersion along the supermode indexes. So super mode axis. So resulting to the fact that we have just two hyperbolas in the instantaneous profile. But more interestingly here is what's going on if we try to generate a soliton. If you try, and so here I show you the results of simulations where I generate a soliton, not exactly at the bottom of the dispersion, of the hybridized dispersion, but somewhere here, right here. So what's going on here? You can see that at some point I achieved to generate a stable structure which starts to rotate in this system, and so it rotates with a given velocity. This velocity is defined by basically the supermode free spectral range, as for example for single resonator, but also since there is also presence of higher order dispersion terms, so there is slight correction to that. And so basically you can see that basically when I take into account only the free spectral range and third order dispersion, I can compute the round trip position, round trip number as a function of time, but it's still kind of different from the simulations because of the fact that there is even more dispersion terms. In terms of spectrum, on a single resonator level, so it would have just a typical comb shape, but it also will breathe because basically the whole system on a single resonator level constantly breathes because of the fact that soliton constantly just arrives and exits this resonator. In terms of two-dimensional spectral profile, what we can see here, we can see that this soliton, it's a disk with a fish-like shape somewhere at the edge of the Brillouin zone. Where it comes from, you can see basically it comes from the fact that the soliton, it's a disk, and it crosses the dispersion profile, and crossing this dispersion profile leads to the efficient phase matching and efficient photon transfer to those photons that can live there and propagate. So it's basically the same thing as Cherenkov radiation in a conventional resonator when we have just a typical parabolic shape with third order dispersion. But what's important here is that when I consider when I try to model two-dimensional topological chain, topological lattice by one-dimensional chain, I'm neglecting basically all this. So basically what's going on, I take into account only modes within the edge band, but I neglect the upper and lower bulks. So basically that's the difference between the one-dimensional chain and the edge states of the two-dimensional topological models, because once I also have edge, so basically the bulk. So what happens here? Similar to the generation of Cherenkov radiation, I would have also transfer photons to the bulk that will basically affect drastically the dynamics of the solitons. Yes, of the solitons. So yeah. Sorry, I don't have time to discuss it for simplified model, and so I'm happy to answer for your questions. Thank you for your attention.
Thanks, Sasha. Yeah, so we have time for questions. Arne.
Yes, hello. Very nice talk, thank you. Could you comment on it, because you have these nice eigenmodes and a lot of degrees of freedom to design now, but what does this actually mean for the driving forces? So you model the driving for each resonator, which is now a vector, and if you want to work with specific nice edge stage, what does this actually imply on the driving?
That's a very good question. Yes, because basically, let me probably, yes. So probably this, not this. Yeah, this picture probably would help. So yeah. So basically, to efficiently couple to one given supermode, you would need to have your to have your driving directly project to it. So basically, you would have to pump each resonator with corresponding phases and basically amplitudes, and it's just not possible. Of course, you're right, and so basically it's one of the main basically problems, and which everyone is neglecting, and me because basically not everyone is understanding what's going on here. Yes, you're right. It's a very good question, and indeed there is kind of no solution, but you need to to efficiently couple to a given super mode. You need to kind of imagine some complicated structures, some complicated pumping schemes, and for two-dimensional lattices of microresonators is just kind of not possible. For one-dimensional, we have some ideas. For example, imagine you have a one waveguide which goes from one resonator to another one, skipping some of the neighbors. So by adjusting the phases in these legs, we can adjust the phase, and try to pump the.
So, but you sorry to interrupt you, but you simulated for the solitons there. So you had, at least for this case, you had already know what the conditions are. Basically, you have to. Okay. For this case, for these which you simulated the solitons, what is the conditions for the driving?
So condition for the driving. So you can see, example here, show an example here. So I was simulating the super mode. Can you see my point?
Yeah,
yes. So it's this dot, which basically indicates that I have oscillation of the phase. So the phase jumps. I have changing of the phase from -pi to pi on the length of 4 resonators. Right. So I had to adjust the phase of my pump so that I have just slight change of the excitation phase for each resonator. Right.
So it's basically same pump with a slight different phase for each coupling.
Right.
Okay. Thank you very much. Very nice.
No problem.
Yeah, we have one more question, Shiwei. I think we have time. Shiwei?
Yeah, hi, Alexander.
Hey.
Hey, yeah, I'm just wondering, because you detect this edge state in your system, is it possible for you to have a computation on the geometric phase here?
So, I mean, you see that geometric phase is just, I mean, it's already in your matrix. I mean, in your coupling scheme, coupling of your matrix. So basically, you need to employ the fact, you need to introduce this geometric phase and the other one, I forgot how it's called. But anyway, to explain why basically edge states occur, to explain, to show that topology explains the physics. But I'm doing this, I'm working the opposite way. I'm just trying to take a topological system in the linear regime. It's already defined all the phases, and then put it into the nonlinear regime and basically show that there is no topology anymore because nonlinear systems are non-linear.
Okay,
and
I got the point. Yeah, thank you. Yeah, I think I got the point. Yeah.
Okay, thank you, Sasha. I think we need to proceed.